over some of the definitions from chapter 26, but this will not take much time. Now, chapter 26 is called Current and Resistance. So we're basically going to go over some definitions. Now, of course, we understand that electric currents is basically charges in motion, right? So I can write electric currents as being charges in motion. Now, heuristically, you can define currents as charges flowing over some time. Okay, so কতটুকু চার্জ একটা সময় দিয়ে পাস করতেছে সেটাই হচ্ছে বেসিক্যালি কারেন্টের ডেফিনেশন. So in that case, I can denote current as I, and I can write it as dq by dt, which denotes how much charge is passing through some finite amount of time. In that case, I can also define q, and I know q is just the integral of dq, and from the definition of the current, I can write it as from some time I times dt. Okay, and this is your definition of the current, and the SI unit for current is of course amperes, which is given as 1 coulomb per second due to its definition of charge by time. Now, if we have a junction, let's say wires connected in a junction like this, and current is flowing, let's say a current is flowing in this direction, through a junction the current will be divided, but total current will basically be whatever current that goes in the junction equal to whatever current that comes out of the junction. So total current will be conserved, and therefore in regards to junctions, whatever current is going in should always be equal to whatever current that is going out of the junction. So এখান থেকে যদি consider করি, this is coming in and these two are going out, and therefore this equation is true. Okay, and now for convention, we always understand that currents are passed through the positive end of the battery. So therefore conventional current comes out of the positive end of the battery, but electrons, for a fact, we know that it travels from the negative end of the battery. Okay, these are already stuff that you already know. Now, furthermore, we can define something called a current density, which we denote as J, and the reasoning of a current density is essentially how much current is flowing, or basically the flow of current. That is what this current density basically defines, and it has the same direction as the velocity of the moving charges, and therefore there is an arrow over the current density. Okay, and we can define this using the current definition as being the integral over J dot dA, where J over here is essentially your current density, and you can rearrange the equation. So if you write I as J dA, where both J and dA are in the same direction, J you can take it out because, like I said, if the current is uniform, then it is, remember that the current density is in the same direction as the velocity of the moving charges. So if the current is uniform, then of course J is also uniform, and hence you can take it out of the integral, and you can write it as JA, and hence you can find an expression for the current density as I by A, which makes sense, right? Basically the density is what defines how much current is flowing through a certain area, so that will basically determine how dense the current is, or what the current flow is. Therefore it is given by I by A. Now next, what we're going to see is the definition of resistance, and this is something also that you've seen before. So resistance, as we know by definition, is given as V by I, which is some voltage divided by current, and it has the SI unit of ohms, right, which is essentially given as V by A due to this definition, which is voltage divided by amperes. And we can also write current definition using this relationship, which we can write it as I equals to V by R, which is essentially saying the same things, And this relationship is actually called Ohm's law. Now, furthermore, you can define the resistivity of a material, and it depends on how much current it can make flow, right? So in that case, this is related to the current density, and it is defined as the following, which is the electric field divided by the current density. And this is the definition of rho, which we are calling the resistivity of a material. Okay. In fact, you can write this also in vector form, and you can write E as rho times J, and therefore you can have a vectorial representation of the resistivity like this. Now remember that resistance is a property of an object, but resistivity is a property of a material. So material upor depend korteche resistivity kemon hobe. So now we can relate resistance and resistivity by the following definition, where R will equal to rho L by A, where L is the length of whatever wire and area is of course given by A, which is the cross-sectional area of the wire, and rho is the resistivity, and that is how R, which is the resistance, and resistivity are related to each other. Now you can also relate the power in an electric circuit. So power, denoted as P, is given as P equals to I times V, which is the rate of electrical energy transfer. So this is essentially telling you that power is the product of the current and the voltage. In fact, you can define it using Ohm's law as well. Given the fact that we know V equals to IR, you can write the power as P equals to I square R just by incorporating V over here as IR. You can also do the same and write P as V square by R, just denoting it in terms of current and voltage. Now that is it for all the definitions from chapter 26. Now we'll move on to chapter 27. Now chapter 27 is called circuits, and this will be the last chapter that we cover for the midterm syllabus. Now for this we're going to look at two types of circuits. One is a single loop circuit, meaning a circuit connected in series, and another is a multi-loop circuit, which is a circuit connected in parallel. So now first, when we talk about a single loop circuit, let's draw it out first. So you have, for a single loop circuit, the following things. So of course you are connected via a battery like this. Let's say you have a resistor connected to it, which has the notation as such, and there flows the current, which again due to convention flows from the positive end, right? And the resistor will have a resistance R, and a current I will flow through the resistor, which is the same I as this, because this is a single loop circuit and therefore the current does not get divided, and the current flows from here as well and into the negative end of the battery. Now we're going to define something over here, which is called the EMF, which is denoted by this symbol, where the EMF stands for the electric motive force, and this is essentially what pushes or pumps the charges to move, and it is also similar to the voltage, and it has the same SI unit, volts. But EMF এর whole idea টা হচ্ছে যে we have a force that pushes the charges out of the battery and makes it move through the system. So this is essentially giving sort of power, or maybe power is the wrong word, but it is sort of giving energy to the charges for moving through the circuit. Okay, and the way we define EMF is via this notation. And since it is sort of like an energy that is pumping the charges, তার মানে হচ্ছে এটা একটা এনার্জিকে পাম্প, মানে এটা একটা energy produce করতেছে. Basically EMF is some energy that is given to the charges to move, right? So therefore if you have, let's say, more charges to be pushed, then you would require more energy, right? So আমি যদি EMF কে ওভাবে চিন্তা করি যে let's say if you have more charges to move, then you will have you will require sort of more energy. So in that case মানে EMF যদি এভাবে চিন্তা করা যায় যে it is something that is making the charges move, then বেশি চার্জকে যদি মুভ করতে হয় তাহলে EMF কমে যাবে, মানে বেশি EMF দরকার পড়বে, right? So EMF will drain. But then if you have more energy, then you will have again regain of that EMF, right? So it's something like that. So in that case I can sort of define it in this way, that if you have more energy you have more electromotive force, but if you have to push more charges then that electromotive force will be drained out. So in that case I can sort of decipher a proportionality relationship and say that EMF is proportional to how much energy is required, and it is inversely proportional to how many charges there are, and therefore I can write the definition of EMF via this expression, which basically states the relationship that you have some energy over there which is given by work done, so some infinitesimal change in energy, and that infinitesimal change in energy is required to push the charges or push the amount of charges dq, and that defines your electromotive force. Now there are two kinds of EMF devices, and what are EMF devices? Basically EMF devices are components of the circuit that produce this EMF, মানে যেটার মধ্যে হচ্ছে এরকম ভোল্টেজ ক্রিয়েটেড হয়, like batteries, like main sources of electrical energy and so on. Now there are two types of EMF devices. One is an ideal EMF device and the other is a real EMF device. Now the difference between the two is that ideal EMF device যখন আমি বলি তার মানে হচ্ছে এটা আইডিয়াল, তার মানে এটার কোনো ইন্টারনাল রেজিস্ট্যান্স নেই। ইন্টারনাল রেজিস্ট্যান্স মানে হচ্ছে এটার ভিতরে যে ওয়্যারসগুলো আছে সেই ওয়্যারসগুলোর মধ্যে কোনো রেজিস্ট্যান্স এক্সিস্ট করে না। তার মানে ও যখন এই ব্যাটারি বা এই EMF ডিভাইসও যখন কাজ করতেছে ওর নিজের থেকে কোনো ভোল্টেজ লস হচ্ছে না, বিকজ উই আন্ডারস্ট্যান্ড যে রেজিস্ট্যান্স থাকলে কিন্তু একটা ভোল্টেজ লস হয়। ওই রেজিস্ট্যান্সটা হচ্ছে রেজিস্ট করার চেষ্টা করে কারেন্ট ফ্লোকে, অ্যান্ড সেই রেজিস্ট্যান্স থেকেই কিন্তু একটা ভোল্টেজ ড্রপ হয়। সো আইডিয়াল EMF ডিভাইস হচ্ছে যেটার ইন্টারনাল রেজিস্ট্যান্স কোনো exist করে না, so no internal resistance. However, we know that is not real, right? Because in reality we do have some resistance, some drag, some friction that will always make the voltage go down. একটু হলেও তোমার resistance exist করবে। So real EMF devices will have internal resistance that will basically bring down the voltage, maybe slightly, but it will. Now we're going to calculate the current in a single loop circuit. তার মানে হচ্ছে এই যে লুপের মতো একটা সার্কিট যেটা এক্সিস্ট করে, যেখানে সিঙ্গেল লুপ এক্সিস্ট করে, বিকজ দ্য কারেন্ট ইজ ফ্লোয়িং থ্রু আ সিরিজ সার্কিট। এরকম টাইপের সার্কিটের মধ্যে আমরা কীভাবে কারেন্ট ক্যালকুলেট করি। Now there are two ways. One is called the energy method. So the energy method, and this is simple, it basically uses the definition of the EMF, where we know that we can rearrange this equation over here and write it as dW zeta dq, right? And I know dq is given by this expression over here that we've done earlier, and we can replace that, and I can write this as zeta I dt. Now zeta I dt can be written as I squared R dt, because essentially remember that zeta has the definitions of voltage, right? And voltage times I is some power. Sorry, I missed a squared over here, but this is some power, and power I can write it as I square R, right? Hence zeta becomes IR as per definition by comparing both left hand and right hand sides. In that case I can figure out what my current will be, and it will just be zeta by R, which is exactly what I expect, because if you remember, I equals to V by R, and since the EMF has the same SI unit and same dimensions as the voltage, this relationship will also hold for the electromotive force. Now, there's another method through which we can find the current in a single loop circuit, that is called the potential method. And the way we figure out this is via something called the loop rule. So let me write what the loop rule is. It states that the algebraic sum of the changes in potential encountered in a complete traversal of any loop of a circuit must be 0. Now, what does that mean? It just means that, potential is conserved, right? So you move from any point and you come back to the other point, algebraic sum should be 0, meaning your voltage should be conserved. মানে তোমার ভোল্টেজ বাড়বেও না কমবেও না if you go through a loop, which makes sense, right? যে আমি যে কোনো সার্কিটের জায়গা থেকে শুরু করে, let's say এই সার্কিটটাই যদি কনসিডার করি, আমি এই জায়গা থেকে শুরু করে আমি যদি লুপটা ঘুরে এসে এইখানে আবার এন্ড করি, then of course আমার ভোল্টেজ should not change, because ওই সেম পয়েন্টেই তো আমি ভোল্টেজটা ক্যালকুলেট করতেছি. So in that case আমার V or whatever I find in that point once I go through the loop should not give me anything extra, and therefore the algebraic sum should equal to 0. This is often referred to as Kirchhoff's loop rule, or also Kirchhoff's voltage law. Okay, how does this work? So let's consider a circuit. So maybe I can write this circuit in this way. Can I have a resistor? And this is how it is. So let's say this is the battery, and of course the battery will supply some EMF, and the EMF will be in the direction of the current, right? Because this is what is moving the current towards that direction. So in that case, since current will flow from the positive end, EMF will also be in the positive end. And let's say we denote some point over here A, যেটা ধরে হচ্ছে আমরা আমাদের ভোল্টেজটা বের করতে চাই, and current হচ্ছে এদিকে flow করবে from the positive end, and it will flow through the resistor in this direction and then finally come back to the battery, right? And this resistor has a resistance R, and remember that this will be a point of higher potential where this will be a point of lower potential. Why is that? Because of course resistorটা হচ্ছে resist করবে and potential একটা loss হয়, like voltage drop করে. তো সেই ক্ষেত্রে of course when it starts out without the resistance, it will have a higher potential. Once the current flows through the resistor, it will lose some voltage, and therefore it will be a point of lower potential, right? So now let's use the loop rule. So the loop rule এর আইডিয়াটা হচ্ছে বেসিক্যালি আমরা যখন একটা কমপ্লিট লুপ করব, while we move through all the components, আমরা হচ্ছে কম্পোনেন্টসগুলোর ভোল্টেজগুলো আমরা কনসিডার করতে থাকবো, যে এটা কি ভোল্টেজ, ইজ ইট অ্যাডিং টু দ্য সার্কিট অর ইজ ইট টেকিং আউট অফ দ্য সার্কিট. সো আমরা প্রত্যেকটা জায়গার পোটেনশিয়ালগুলো ক্যালকুলেট করব. সো নাও ইফ ইউ স্টার্ট ফ্রম পয়েন্ট এ হ্যাজ সাম আরবিট্রারি পোটেনশিয়াল, লেটস কল দ্যাট VA. সেটা আমরা কি জানি না, আমরা জাস্ট এটা ধরে নিচ্ছি. নাও লেটস গো থ্রু দ্য লুপ in a clockwise direction, okay, in this direction. So in this case, once I move through the circuit, remember আমি প্রত্যেকটা কম্পোনেন্টের কিন্তু potential consider করব. So point A তে আমার VA, and then I go towards the battery. The battery has some potential, but this potential is given by the EMF, right? So therefore I can write there will be an algebraic sum of the EMF. Now next question to ask is that once I encounter a component, next আমি কিভাবে এটাকে algebraic sum করব. Now remember যে কম্পোনেন্টগুলো সার্কিটকে অ্যাড করবে, মানে সার্কিটে পোটেনশিয়াল অ্যাড করবে, সেগুলোকে আমি প্লাস দিয়ে লিখব, আর যে কম্পোনেন্টগুলো সার্কিটের পোটেনশিয়াল নিয়ে নিবে বা ইট উইল ডিক্রিজ দ্য পোটেনশিয়াল অফ দ্য সার্কিট, I will write them as minus. Okay, so therefore when I go through the battery, I know of course it adds to the potential, right, because এটা একটা potential supply করে, তো সেই ক্ষেত্রে I will write plus the EMF. Now next কাজ হচ্ছে যে I move through the circuit and then I encounter the next component, which is the resistor. And I know for a fact that the resistor actually takes away from the circuit, right? So this should be a minus. And resistor through the key voltage বা key potential হচ্ছে বা key potential is being taken out is given by V equals to IR, and therefore I can write it as I times R, where I is the current flowing through the resistor and R is the resistance, right? And then I move through and then I come back to my same position through the loop, and therefore this should equal to VA, right? So in that case, basically these are where I started, my initial point, and this is my final point, and therefore they should be equal to 0 because the algebraic sum through a loop should be the same, equal. So in that case, from both sides I can consider that VA is gone, and therefore this equation becomes zeta minus IR equals to 0. And essentially this is what the algebraic sum is, that whenever I go through the components, you see the components are the battery, which is given by EMF zeta, and IR, which is the resistor. প্রত্যেকটা কম্পোনেন্টের থ্রুতে যে পোটেনশিয়াল টা ফ্লো করে, যে পোটেনশিয়ালটা আসে, সেটার algebraic sum will always be equal to 0, and this is what I get. In this case, we can solve this equation to find the current in this single loop circuit, and from here we will see that I actually is equal to this, which is the same thing that we expect. Now another question people ask is that why did we take the loop to move clockwise? আমরা তো counter clockwise ও যেতে পারতাম, like we could move in this direction. Of course we can, but it would give you the same result. So for example, if you moved counterclockwise, again let's start from the point A. In that case VA আমার একটা point থাকতো, right? And then I would move in this direction, so it now moves against the current. So যেটা আমার আগে মাইনাস ছিল, যেটা আমি মাইনাস IR হিসাবে লিখতাম, সেটা এখন আমার প্লাস IR হয়ে যাবে, right, as I'm moving against the current direction. So I have to take a minus মানে minus I, and যেটা minus IR ছিল সেটা এখন plus IR হয়ে যাচ্ছে. And then I move through and come to the battery over here, and battery direction যেটা opposite to my loop direction. In that case যেটা আমি আগে plus zeta পাইতাম সেটা এখন আমি minus zeta পাবো, and this will be equal to VA, which is the point that I started with. And again you can do the same thing, you can cancel VA out from both sides, and you get minus zeta plus IR equals to 0. Again, solving this equation will give you the same thing, which is I equals to zeta by R, and this is what you get. So now I know for a fact then that whatever direction you choose the loop to go to, it does not matter, you can apply the loop rule in any and either direction. Okay. Now let's consider that you're not dealing with an ideal EMF device, but you have internal resistance. Okay, so in case we have internal resistance, how do we construct these equations, these loop equations for a single loop circuit? Okay, so now let's consider the circuit again. So remember that I had a battery, so let me draw the resistor first. But now this battery has an internal resistance, তার মানে ভিতরে একটা resistor আমি add করতেছি. So let's say this is the positive end of the battery, this is the negative end of the battery, and there exists an internal resistance, and EMF will be in the direction of the current. So the current is flowing from the positive end like this, right? But there exists an internal resistance, so internal resistance ke ami boli defined as small r. This resistance, which is the external one, which is of the resistor, let me denote that as big R, capital R, And now we are going to apply the loop rule. Let's do it clockwise. Like I said, the direction does not matter, so we do it clockwise because it is in the direction of the current, so it's easier to do computations like that. Okay. So now let's define some beginning point. Let's say this is here, some beginning point A, and let's say we want to look at this point A and move through the circuit. Okay, so point A থেকে যদি যাই আমি VA লিখতে পারি, but I know for a fact that যখন ঘুরে আসি V আর VA কিন্তু cancel out হয়ে যায়, so essentially আমার VA টা is useless, so I can just only focus on the components. So in that case প্রথমে যে component আমি encounter করি সেটা হচ্ছে ব্যাটারিটা, so therefore first EMF or first potential is a positive potential because it is in the direction of the loop. তারপর নেক্সট যে কম্পোনেন্ট আমি মানে ফোকাস করব সেটা হচ্ছে দি ইন্টারনাল রেজিস্টার, রাইট? সো ইন্টারনাল রেজিস্ট্যান্স যেটা এক্সিস্ট করতেছে স্মল আর, সেটার জন্য যেটা পোটেনশিয়াল ড্রপ করবে সেটা আমাদেরকে কনসিডার করতে হবে। অ্যান্ড সিন্স দিস ইজ আ রেজিস্টার ইট উইল টেক অ্যাওয়ে দ্য পোটেনশিয়াল, রাইট? সো আই উইল হ্যাভ আ মাইনাস কারেন্ট ইজ ফ্লোয়িং টাইমস দ্য রেজিস্টার IR। না সেকেন্ড যে কম্পোনেন্টটা আসি আমি সেটা হচ্ছে এক্সটার্নাল যে রেজিস্টারটা সেটার জন্য একটা পোটেনশিয়াল ড্রপ করবে, সো আই উইল গেট মাইনাস IR and this will equal to 0 because the algebraic sum equals to 0. Now if I want to solve for I just by rearranging this equation, I will see that my I becomes R plus small r, which is almost the same as this, but it incorporates the extra resistance that is due to the internal resistance. Now if the internal resistance R is equal to 0, it boils down to the current that we would see for an ideal EMF device, right? So in this case we see that when we have a single loop of resistances, in that case you can basically connect all the resistances in series. Essentially single loop মানে কিন্তু একটা সিরিজ সার্কিট, কারণ আর কোনো ব্রাঞ্চ নাই যেটার ক্ষেত্রে আমাদের অন্য কোনো লুপ হচ্ছে না। তো সেই ক্ষেত্রে আমি একটা রেজিস্ট্যান্সের জায়গায় কিন্তু মাল্টিপল রেজিস্ট্যান্সেসও ইনক্লুড করতে পারি, বাট ইন সিরিজ, রাইট? সো ইন দ্যাট কেস আই ক্যান হ্যাভ আ সার্কিট দ্যাট লুকস লাইক দিস, where you have a bunch of resistors connected in series. Let's say this is R1, R2, R3. This is your battery, so of course you will have an EMF. This is a plus point and minus point, and I will have resistors connected in series. Now similar to capacitance, I can also consider all the contributions of this resistor coming from all of these resistors as coming from one resistor with an equivalent resistance. Okay, so I can convert this to a single circuit with one resistor which has an equivalent resistance of all of the resistors combined in series. So how I would do that is, let's consider first the current which is যেটা আমরা এতক্ষণ করতেছিলাম loop rule যেটা সেটা on this resistor, and then we can find out what actually the equivalent resistance relationship is with R1, R2 and R3. So আমরা loop rule করি। So for this circuit over here, let's consider that first আমি যদি এই ডিরেকশনে যেতে থাকি, the first component I will face is the EMF device, so EMF যেটা, and then second component হচ্ছে RI মানে R1, so this will basically take away the potential, so I will get a minus I R1. Same for the second one, R2, and thirdly same it, and this will all equal to 0. And you see that I have the same I because since this is a series circuit the current is not divided, so basically same current flow করতেছে from all the devices, right? Then I can rearrange this and I can solve for I, and I will get the EMF divided by R1 plus R2 plus R3. Now this is the total EMF and this is the total current, so in that case I can write this equation, and remember that I can transform this whole circuit to this circuit over here, where I can basically write all the resistances as one resistor with an equivalent resistance, right? So এটার জন্য আমি যদি loop রুলটাও কনসিডার করি, I know I will get something like this, and therefore if you compare the two, and এটার জন্য যদি আমি I বের করি, I know I will get R equivalent over here, and if you can compare these two expressions, I know for a fact that R equivalent will just be equal to R1 plus R2 plus R3. Okay, and this is the resistances for an equivalent resistance in a series circuit. So now you can convert this to you can consider as many resistors you want, and in that case R equivalent will be just the summation over all of the resistances as such. And this is the relationship for a series circuit when you're considering only a single loop circuit like this.